Good morning, everybody. Hope you're all healthy and safe at home. Let us continue with our section on Green's theorem. So, in the previous lecture and all, we had discussed what was Green's theorem, and we had seen an example which depicted how to use Green's theorem. Now we will move on to a few more examples which are given in your textbooks. So let's see example 2. We are asked to evaluate the line integral over the closed curve x raised to 5 plus 3y dx plus 2x minus e raised to y cube dy, where c is given to be the circle, but the curve is x minus 1 whole square plus y minus 5 whole square is equal to 4. That is, it is a circle with center 1 and 5 and radius 2. So figure 9.12.5 depicts the curve C. You can easily see that. Now let us see how we can solve this problem. First of all, we'll find what is p of xy. P of xy is x raised to 5 plus 3y, and q of xy is 2x minus e raised to y cube. Then we will find what is the partial derivative of p with respect to y. What will it be? It will be equal to 3. And what is the partial derivative of q with respect to x? It will be equal to 2. So clearly all these are continuous in the given region R, right? There's no point of discontinuity here. All are continuous functions. So by Green's theorem, we can conclude that the line integral over the curve C can be written as double integral over R. Dou q by dou x is 2. 2 minus 3, that is minus 1, into double integral over R dA. Now we have learned in the previous section that double integral over R dA actually gives the area of the region that we are considering. Now C is a circle. It is familiar for us that the area of a circle is nothing but pi r square. So it is, the evaluation of this line integral becomes very easy. It is just the value of the area, that is we know the radius is 2. So the area of the circle will be pi into 2 square, that is 4 pi. So the integral value is minus 4 pi. So this is a very important or a useful result that we can use. That is, by Green's theorem we can easily calculate the line integral over any closed curve. Now let's move on to example 3. In this example we'll discuss about the work done. We all know that we have discussed in previous sections and all with the work done of any region of any force which is given to us can be calculated by just integrating f dot dr, right? So let's see how we can do this. We are given a force F is equal to minus 16y plus sin x square I plus 4 e raised to y plus 3x square j, acting along the closed curve which is shown in figure 9.12.6. So you can see it's like a part of a circle. So you can see the figure, you can see the curve which is given to us. We are asked to find the work done. Now we know that work done is nothing but line integral f dot dr. Okay, so f dot dr means df is minus 16y plus sin x square I plus 4 e raised to y plus 3x square j, dot dr is dxi plus dyj. So comparing them, we'll get minus 16y plus sin x square dx plus 4 e raised to y plus 3x square dy. So this becomes the form which is similar to us, familiar to us to use Green's theorem. So we can see that p of x comma y is minus 16y plus sin x square, and q of x comma y is 4 e raised to y plus 3x square. So what will be dou p by dou y? It will be minus of 16. And what will be dou q by dou x? It is 6x. So by Green's theorem, this line integral, that is the work done, will become double integral over R 6x plus 16 into dA. Okay. Now we can use the limits of x and y, but if you see this figure, you can easily see that it will be much more easier to solve using the polar form, because using polar form R varies from 0 to 1. And what will be the variation of theta? Theta will be, this is actually pi by 4. So pi by 4, and this angle will be pi minus pi by 4, that is 3 pi by 4. So theta varies from pi by 4 to 3 pi by 4. Right? So from the region, it will be much more easier now that we know how to solve double integrals using polar coordinates. So I think it will be much more easier to solve it in this manner instead of finding the limits of x and variation of y, because variation of y will give us the y limit from varying from 0 to root of 1 minus x square, and also that will become a bit more complicated. So it will be easily solved using polar coordinates. So let's see, w will be integral theta varies from pi by 4 to 3 pi by 4, and r varies from 0 to 1, and x, there is a term called x, so that will be 6 r cos theta plus 16, and don't forget dA will be r into dr d theta. So how can we solve this? The value will be 6 r cos theta, this will be r square by 3, so no, sorry, there is 6r square, so it will be r cube by 3, so that will be 2r cube cos theta plus r square by 2, so that will become 8r square, and varying from 0 to 1, so that will be 2 cos theta plus 8, okay, into d theta. So 2 cos theta plus 8 d theta will become 2 sin theta plus 8 theta, varying from pi by 4 to 3 pi by 4. So by solving that, we can obtain the value to be 4 pi. So this is how we can easily find work done. So we know we have calculated work done in previous sections also, but if we are given a region as such, a closed curve, then I think it will be easier for us to use Green's theorem, because Green's theorem is applicable for all curves which are closed, simple closed curves. So that's it. We shall wind up with today's section. Thank you. Stay home and stay safe.